Okay. I apologize about that. My youngest one just woke up from a nap and totally jumped and ruined the movie. So, continuing on, welcome to part two. If this is a strong base on my arm, then every single base molecule is going to pull protons out of my arm. So, these protons are coming out of my arm, and that's why it burns. That's why it pulls it out of the cell membranes of the cells in my arm and pops them, and that's why your skin like melts off, is because the cell membranes get popped as these steal protons. So if every single one steals a proton, that makes it a strong base. Again, strong just means the number of molecules that actually react. But if we reset, so a strong one, every single one does. If we reset, and instead of a strong one, again, let's not talk strong. Let's switch over to weak. A weak base, it's much like a weak acid, where it gets splashed on my arms. Oh my gosh, you guys are terrible. And only one pulls a proton out of my arm, and the other ones are, I'm not that hungry. I'm on a diet. Yeah, I'm really counting my calories, or I refuse to get near a carb, or whatever the diet is that day. But most of the molecules of the base do not react. They are still hungry, but not actively hungry. If they were actively hungry, they would pull protons out of my arm. They just have like a mild, they're like bored hungry, where it's like, if there was an easy treat, I'd just go ahead and eat it. But if I have to like make it myself, I'm just gonna not eat. And that's where these base molecules are. So this whole thing would be considered a weak base because only one got around to actually stealing a proton from my skin. And so there would just be a slight mini sizzle. And the rest of them are totally fine. Like this part of my skin is not being reacted with. It's just got a base on it and no burn. So the difference between a strong acid and a strong base versus a weak acid and a weak base is just the percent of molecules that actually react. Now that's all I want to cover today. So I'm going to answer the point, but there's going to be a bit of a review after that. So after you answer the point, or after I answer the point, you write it down, I would keep watching the video and I would kind of pay attention to the stuff that I write after it. But if you don't want to, you don't have to because it's review. Okay, so how are strong acids and bases related to weak ones? Strong acids and bases have more particles react. That's an E. Have more particles react than weak ones. Okay. Oh, just barely. I can't see the period. There's a period at the end. You just can't see it. So the difference between strong acids and bases and weak acids and bases is just strong ones more react. They're just more volatile. They either donate more of their acidic hydrogens or they pull more protons out of their environment. There it is. So write that down. Pause if you need to, because I'm about to erase it and move on to a review about pH, hydronium and hydroxide concentrations. So pause. Welcome back. Okay. So I just want to quickly go through the math with pH, hydronium, and hydroxide concentrations, because that's something that sometimes throws students for a loop. So let's just get a little charty chart put up. So we're going to put pH values here. We're going to put hydronium values here, and that's hydronium concentrations, and hydroxide concentrations here. And we're just going to do a couple, and then we're going to attach it to strong acids and bases. So let's put some lines on. There you go. Maybe even extend these, make it like a legitimate table. And I'm just going to put a couple random values down. So I'm going to put, I don't know, 3 here. And I'll put, I don't know, 10 to the negative 9 there. And I'll put, I don't know what, 10 to the negative 2 here. And I'll put, I feel like got to put 7 somewhere. All right. And last but not least, I'll put, I don't know what, 10 to the negative 14. There we go. So we're just going to fill in the rest of this table. There's enough information now on this table to fill in every single box. So we're just going to kind of do that. That's what we're going to do. So remember, between pH and hydronium, there's no actual math. This is just shorthand. pH is just shorthand for 10 to the negative. So pH of 3 means has a hydronium concentration of 10 to the negative 3, which also means that 10 to the negative 9 is a pH of 9. So it goes both ways, right? This just go 10 to the negative. This just take the positive aspect of the exponent and write it down. And here we have some math. So I'm going to do this in a second, but let's bang these out also. So what do we have here? We have a pH of 7, so that becomes 10 to the negative 7. Again, no math there. And down here, we have 10 to the negative 14, so I just quickly write 14. Okay, so again, there's no math between pH and hydronium because that is the power of hydronium. That's what it originally was. And it's just shorthand for a concentration of hydronium of 10 to the negative. That's what pH means. Now we've got a little bit of math. Hydroxide, whatever the exponent is in hydroxide, and hydroxide looks the exact same way. It's going to be 10 to the negative something. So I can actually just write those in. So we'll do that all the way down. It's 10 to the negative something. I don't know what that something is, but it's 10 to the negative something. And this something plus 3 has to equal 14. So 14 minus 3 is 11, which means 11 plus 3 is 14. Boom, I got it right. And now 9, I've got 9 plus something is 14. So 14 minus 9 is 5. 5 plus 9 is 14. Nailed it. And now we're going backwards. Now we've been given the hydroxide and we have to go back to the hydronium. Well, 14 minus 2 is 12. So it'd be 10 to the negative 12. All right. And, oh, wait. We can just fill this out because there's no math here. And I just write 12. Just as simple as that. Remember, this is the no math side of things. And 14 minus 7 is 7. Hey, that's right. This is neutral. And what that means is that the hydronium and hydroxide concentrations, if you throw this in water, are the exact same. It's no more acidic or basic because hydronium is how acidic something is, hydroxide is how basic it is, and lo and behold, when it's neutral, those are identical. And then last is 14. 14 minus 14 is 0. So this is the one time where it's not negative. If you do that on a test or a quiz, I'll take partial credit because there is no such thing as negative 0. So this is the one time whenever it's 14, this is the one time you wouldn't have negative. Everything else would have a negative. So what does this mean? Well, let's change one of these and talk about the strong. Instead of 3, I'm going to put 0. And so that'd be 10 to the negative 0. Oh, wait, there's no such thing as negative 0. So it's just 10 to the 0. And then this becomes 10 to the negative 14. Okay, so this is what we call a perfect acid. And this down here is what we call a perfect base. So this is as strong an acid as you can get. This is as strong a base as you can get. And this is neutral. And I really just kind of want to look at these. So let's see, 10 to the 0. What is that if I don't write it as an exponent of 10, but actually write it out as a number? The answer is 10 to the 0, well, anything to the 0 equals 1, which means this is 100%. This means that if I throw a perfect acid into water, every single acid molecule is going to react. 100% of those molecules are going to come in, they're going to react, they are going to throw their proton on the thing, stop being an acid, and float off. 100% of them are going to donate their proton. Okay. And what about what about here? 10 to the negative 14. Well, 10 to the negative means that it's 1 over, and 10 to the 14 is 14 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this means, if I put in the little commas, 10 to the negative 14 actually equals this fraction. That's what this simplifies to. And that's hundreds, thousands, millions, billions, trillions. So for every 100 trillion water molecules, one will be changed into hydroxide, because this is hydroxide. So that means in a perfect acid, you can still have a slight reaction with a base, but what's going to happen is 99,999,999,999,999 are not going to react, and one will. So this whole thing, this basically equals 0. So in a perfect acid, 100% of the acid reacts and basically 0 of the base reacts. That makes sense. That's what I'd like it to be. And then we notice that this just flips. Now the 1 over 14 zeros, which is basically 0 here, happens there, right? And this 10 to the 1 is 1, or 100%, just barely fitting on the screen. So in a perfect base, 100% of the bases, so that means every single base molecule rips a proton out of its environment, eats it, which of course then makes it not a base anymore, and leaves happy. 100% of them. Because 10 to the 0 is 1, which equals 100%, right? And basically none convert. But what about these? What about these values? This right here. That's the last thing I want to talk about. Well, it's 10 to the negative 7, so let's move this over a little bit so I have a little right in the room. Well, again, a negative exponent just puts it under 1. And 10 to the 7 is 10, 1 with 7 zeros. 1, 2, 3, 4, 5, 6, 7. So what that says is for every hundreds, thousands, millions, for every 10 million molecules of water, one's going to get converted. And that's true for here too, because these are the exact same. So this is also, so for every, so if you had 20 million water molecules, one's going to become hydronium, one's going to become hydroxide, and 19,999,998 are just going to stay water. And that's what, because for every 10 million, one's going to become hydroxide. For every 10 million, one's going to become, hydroxide, hydronium. One's going to become hydronium, one's going to become hydroxide. And all the other ones, all the other molecules are just not going to react. So, how acidic is it? Well, it's that acidic. Which really isn't a very big number. That is really, really, really small. If somebody said, we're going to give you that raise this year, I'd be like, yeah, that doesn't even round to like a fraction of a penny. You're basically giving me nothing. And then my boss would laugh and be like, yeah, well, that's what you deserve. And that might be true. So for every 10 million molecules, only one's going to react and make it acidic, and the same thing here, and that's neutral. So again, this graph is not this kind of a graph. It doesn't go this way. It goes, it's an exponential graph. These numbers are exponential. So things are going to get real big and real small only at the ends. And that's how that works. Okay, that's all I got for you today. Good luck.